Hello again. Hopefully this is going to be a short video. Currently I have all these meters tied in series and they're attached to our large power supply. See, I have a couple of clocks out here to kind of monitor the time as this test progresses. This is the UT61E that we just got through modifying to run at 20 amps. Some of these meters can't run at real high current. You'll notice on the SEM DT9939 it is actually marked on the front here 20 amps for 30 seconds max every 15 minutes. So I can't expose all these meters to 20 amps like I can the UT61E. But what I'm going to do is set these to roughly 5 amps and then we're going to let them set and we'll see how much they drift. Okay, I think I have all the meters auto power offs or shut off right now. Alright, so I just jotted down what their values are. What I'm going to do is select these all to relative mode. So now they should all basically be reading 0. Now we'll just let them set for a while. And again, I am driving these off of a constant current source, so I have a very low ppm sense resistor that I'm using in the control loop, and that is my reference. So you can see it looks like they're all basically stable now. What I'm going to do is increase the current to roughly 10 amps. What I want to do is just basically build some heat inside of the meters. Okay, now what I'm doing is dropping them back to 5 amps. And let's just see how all these do at returning back to their 0 point. Looks like the camera batteries died, but at least you've got the clock so you can get an idea how much time has lapsed. Looks like everything's pretty much settled in. I may not have given the UNI-T enough time at 5 amps to settle, because it's definitely, I think, got a little bit of hysteresis. I would expect these two to be fairly close, but you can see there's definitely a discrepancy of about 4 milliamps. It's not much, but it's definitely measurable. See, I just took them all off of rel mode. They're now in absolute. And that 61E is definitely reading a little higher than what it was initially. What I'll do is give it a little bit longer. We'll see if it'll cool down any further. I'd say it's definitely reached steady state. What I'm going to do is disconnect everything except this 1 meter. Now what we'll do is we'll let this heat up to whatever it gets to at 20 amps. And we'll go ahead and reattach all the meters and we'll let it idle back down to 5 amps. Let's just see if it falls back into the 12-ish milliamp area or not. So I think that's probably been pretty close to 5 minutes now. What we'll do is hook the other meters back up. Alright, now I'm setting it back to 5 amps. Let's just see how close this gets back to 5.012. There's a fair amount of thermal mass in that meter now with all that copper I've added, plus the larger shunt. And then I have the Teflon spacers around it, so it's not going to cool quite as fast. It's part of the reason that we're seeing such a slow thermal response with it. Well, I'd say we are definitely at equilibrium again. if we could keep the batteries in the camera working. Anyway, I think what I'm going to do is set up another test where we take just the shunt, put it back in our clamps, and I'm going to change my software so we can just cycle that piece of it and then see how that behaves by itself. So what I'd like to do next is evaluate just the shunt by itself. So what I've done is I've made another shunt. This is basically a replica of the part that I have in here. Before I do that, a couple of things I'd like to mention. Somebody talked about basically adding a resistor in series with this pot to try to desensitize it. There's actually a resistor on the back side of the board. This is our dead UT61E, you can tell. So there's this resistor right here. It's marked RA, and this is a 10k ohm resistor. And this is in series with the potentiometer going back to ground. You can kind of see the trace working its way down this way. And the potentiometer has a resistance of 2k, so it's a 2k to 10k divide ratio. So I went ahead and I removed the 10k out of our working meter, and I've gone ahead and replaced that with a 20k. I tried a 30k, that was just a bit too much. You can see after all that running at 20 plus amps, there's very little damage to our setup so far. I think part of the problem was having this piece of Teflon in here is actually increasing the thermal lag of the meter. It may actually perform better without this. I just don't know if it's worth the risk of having that heater sitting here cooking the other parts. So this is looking at the data for all the fuses I tested so far. You can see I've ran a couple more since the last time I showed this graph. And this one at the bottom, you can see it's sub 8 milliohms. It's very similar to the fuse that I have in the meter now, which I showed you the data sheets. This is a 20 amp part. This is the 25 amp version of that fuse. So there's a little bit more to be gained. I don't know if I would risk running a 25 amp fuse in here. I think it's better to keep it at 20 amps and just give up some of the efficiency. You can see I have my second shunt installed in the test jig. You can see I'm switching between 8 amps for 10 seconds and 30 amps for 5 seconds. What I'll do is just let the system cycle like this for an hour or so, and then we'll capture all this data into a file, and then we can post-process it and just see what the effects are. So let's have a look at the data that we just collected. So this is looking at the resistance of the shunt. And if I zoom in just a little bit, we can see there's definitely two discrete points as we're switching between the two different current levels. And you can see the higher current has a much more stable resistance versus the low. And I expect that that's caused by the noise of the power supply. So what I can do is take this data and I can slice it into each one of these cycles. And then what I can do is take each individual cycle and overlay it on top of the next cycle. And that'll give us an idea of how this is actually changing in time. So again, this top graph is our raw data. You can see there's about 400 cycles that we've ran. This is again over the course of about an hour. At the bottom graph you can see this is all these cycles overlaid on top of each other. The reason they are kind of smeared is because my window width is wider than one cycle. So if I drop this down to say about 150, this is looking at the valleys and this is looking at the peak. Next, what we can do is plot the histogram of this data. And you can see I have two discrete peaks. And again, these two discrete points are because I'm switching between the two current levels. So if I shorten this down even further, let's go to 100. Oops. Let's go to 100. Now I'll go to histogram. You can see we've basically taken out the other peak. So without the switching, you can see that the standard deviation has dropped quite a bit. It's now 22 microohms. So another thing we can do with this is view this in 3D. And so the vertical axis is looking at the resistance. Going across this direction is the number of samples that were in each cycle, and going this direction is the number of temperature cycles. You can see the blue area in the center. This is where we are cooling down the shunt. It's very consistent. These two outside edges, again, this is where we are in the process of cooling. This is looking at the side view of the data. That's basically rotating the data this way and then looking in this area right here. And you can see there's basically no real trend to this. It's starting to go down, it looks like, but then it recovers and it's starting its way back up. This could very well be the furnace cycling in the house. If we look across a single sample, again, this is very flat, which we'd kind of expect. Just a lot of noise in it. If we go back to the slice, and we'll go ahead and look at the peaks. Again, the area that we're actually heating, it's very consistent. You can see it's definitely getting a little hotter in this area, and it's bringing the bottom area up where it's cooling down. But you can see how much the resistance is actually changing. It's very little from the bottom. It's 12 milliohm, and at the very top it's 12.2 milliohms. So it's actually very stable. I should mention too, this manganese is not actually all that great of a material for temperature stability compared to what would be used in a modern type shunt. So I actually looked at making an even better shunt for the UT61E, but because of the volume would be so low, I'd end up spending more for that material than I paid for the highest dollar meter I bought. You can see with LabVIEW I can zoom in and out. Obviously you've seen the rotation, and you can also pan. Okay, you can see I have the large shunt out again, and the Brahman is placed across it, and then this is in series with the UT61E. What I'm doing is cycling the current up to 30 amps across the UT61E, but just for a very brief time so we don't damage the fuse in it. And what I'll do is I'll just let it cycle like this for a while, and we can get an idea how much this meter drifts now. Well, this thing's been running about an hour now. It looks like there's some drift with it. What we can do is turn off the power supply. Tell you the bad part about making these long videos is I don't have a way to run the camera for extended lengths of time. Anyway, it looks like the 2 meters are still reading basically the same value after all that. I mean, to be honest, I think what we've learned from all this testing is that if you're going to try to make a meter run at 20 amps, what you probably want to do is start with a smaller shunt and then gain that up. Unfortunately, this chipset that's used in the UT61E does not apparently have a programmable gain amplifier for the shunt. So you're kind of stuck with that 0.01 ohm resistor. So you'd have to add an external op amp to gain that up. But then you could get the power dissipation down. Of course, that would be a lesser problem than with the heat. And there's our shunt, fuse, added copper, a lot of thermal mass, very slow response. And again, swapping out the resistor on the bottom of the board from a 10K to a 20K ohm, making the adjustment a little less sensitive. This is the original shunt out of the UT61E. This is the one that I've made to replace it. See quite a bit more surface area with this. This is a test one that I made as well. Now we have this. This is my first attempt at using it. This is actually a tack. See, I cut the sharp end off and I used the flat spot here and I just MIG welded that wire right to it. The shunt actually worked pretty good, but I wanted to find a better way to mount it into the board than the tack. So this is my attempt at silver soldering it. That seemed to work okay. So this is our new shunt. See it tucked down in there. You can see it has even more surface area. And again, we can put the cover over the top. So currently I'm not using my shunt. I have both the Bryman and the UT61 in series. You can see I have the clock out again. I'm applying 5 amps through both meters. I'm just going to let them sit now for a while. And let's just see how the UT61E will drift now with the new shunt. Stupid camera. Alright, so the meter's been running almost an hour, at least 45 minutes. What we're going to do, let's just do that a little differently. I'm just going to jump out the Bryman. See, our current control jumped up for just a sec. And I'm going to do two things. I'm going to change out the batteries in the camera because it just died again. And then I'm going to increase the current to 20 amps and we'll let it sit for a little bit. Okay, so I've had the meter sitting for about, well, I don't know, at least 15 minutes at roughly 20 amps. So what I'll do now is I will reconnect our Bryman after I set the current down to something reasonable. And just make a quick switch. You can see it's reading a little bit high. I'll just adjust it up to an amp. There's quite a bit of noise on the system, but it looks like our UT61E settled down fairly quick. So what I'm going to do is just turn off the power supply. And let's just have a quick look at this. As you can see, no discoloration at all. It definitely handles the heat quite well. But again, the watt density on this shunt is going to be quite a bit lower than the previous ones that we had tested. So yeah, looks pretty good. So after several modifications, our little UT61E is turning into a fairly nice meter. Of course, we have our shunt now and our 20 amp fuse. Of course, we've replaced the MOVs, the PTCs, we replaced the fuse holder. We installed some TVS's and we installed some current limiting in there for the ESD protection. We added a backlight. We also did a temperature compensation mod to it. This meter actually works pretty good now. Well, I think that's going to be it for all of my shunt modifications, so I hope you enjoyed the video. I'd like to welcome you new followers. Glad to have you on board. Till the next meter. Later.